Before you buy an electric vehicle, the price on the sticker is what grabs your attention. But if you already own one, or if you have spent any real time talking to EV owners, you know the real anxiety starts much later. It starts years down the road, when warranties fade, when range slowly slips, and when one unanswered question begins to dominate every long-term calculation. What happens when the battery becomes a problem? For many drivers, battery repairs, degradation, and unpredictable replacement costs remain the single biggest financial unknown in electric vehicle ownership today. Even as EVs become cheaper to purchase, the fear of a massive battery bill never fully goes away. And that fear is not imaginary. Right now, one serious battery issue can erase years of fuel savings in a single service visit. But behind the scenes, Tesla is quietly exploring a different path. A battery chemistry that does not behave like today's lithium-ion packs. A chemistry that tolerates heat instead of fearing it. A chemistry that survives abuse rather than demanding perfect conditions. And a chemistry that could finally change how long an EV battery lasts, how often it needs service, and how much it costs to own an electric vehicle over its full life. What if your EV battery did not rely on complex liquid cooling systems to stay safe? What if it could fast charge repeatedly without accelerating degradation? And what if repairing the battery no longer meant replacing the entire pack, but only the portion that actually wore out? That is the conversation starting to form around aluminum-ion batteries. Welcome back to TESLARIS, where we do not chase hype, leaked renders, or exaggerated promises. Here, we break down Tesla technology through engineering logic, manufacturing reality, and real-world ownership impact. If you care less about flashy concepts and more about what actually lowers your cost per mile over time, you are exactly where you belong. To understand why Tesla's interest in aluminum-ion batteries matters, we need to start with the most expensive and most misunderstood component in any electric vehicle: the battery pack itself. In today's Teslas, the battery pack is not just heavy. It is complex, sensitive, and tightly controlled. A typical lithium-ion battery pack weighs well over 1,000 pounds. It operates within a narrow temperature window. It relies on liquid cooling loops, pumps, valves, sensors, and software safeguards just to stay within safe operating limits. When everything works perfectly, the system is impressive. But when something goes wrong, costs escalate fast. Battery-related repairs remain among the most expensive events an EV owner can face. Even relatively small thermal issues or imbalances can force module-level replacements. Depending on vehicle, region, and warranty status, those repairs can climb into the thousands or even tens of thousands of dollars. And because lithium-ion chemistry is unforgiving, manufacturers design packs conservatively. When in doubt, parts are replaced rather than repaired. Aluminum-ion batteries attack this entire problem from a different direction. Unlike lithium-ion cells, aluminum-ion chemistry is inherently more thermally stable. In laboratory testing, aluminum-ion cells have demonstrated the ability to operate at extremely high temperatures without entering thermal runaway. Where lithium-ion cells can become unstable if cooling fails or degradation becomes uneven, aluminum-ion chemistry remains far more forgiving. That single difference has massive implications for vehicle design. If Tesla can safely deploy aluminum-ion batteries in production vehicles, it could dramatically reduce the need for heavy liquid cooling systems. In some designs, it could partially eliminate them altogether. Cooling hardware alone can weigh hundreds of pounds at the vehicle level and introduces dozens of potential failure points over a long ownership lifespan. Every hose, pump, connector, and seal is something that can leak, fail, or age out. Remove enough of those components, and you reduce maintenance not just today, but a decade into ownership. From an owner's perspective, fewer cooling components means fewer surprise repair bills and fewer trips to the service center for issues that have nothing to do with driving. But thermal stability is only one part of the story. Another critical advantage of aluminum-ion batteries is charge and discharge resilience. In controlled environments, aluminum-ion cells have demonstrated the ability to withstand an extraordinary number of charge cycles with minimal capacity loss. While real-world automotive versions would never operate at laboratory extremes, even a conservative fraction of that cycle life would outperform most lithium-ion packs on the road today. For context, many lithium-ion EV batteries begin to show noticeable degradation after a few thousand full cycles. Aluminum-ion technology has the potential to push usable cycle life far beyond that. For the average driver covering typical annual mileage, that could mean a battery that lasts well past 300,000 miles without requiring major capacity restoration. And that is where the ownership equation truly changes. Instead of planning for a battery replacement late in the vehicle's life, aluminum-ion batteries could realistically outlast the rest of the car. Motors, suspension components, interior materials, and electronics would wear out first. That flips the depreciation curve. It changes resale value calculations, and it reshapes how long people feel comfortable keeping their vehicles. For buyers who hold onto cars longer than the typical short ownership window, this matters more than peak range or acceleration numbers. It is about confidence. Confidence that the most expensive component in the vehicle is not a ticking time bomb. Material sourcing plays an equally important role. Aluminum is one of the most abundant and recyclable materials on the planet. Unlike lithium, nickel, or cobalt, aluminum supply chains are mature, geographically diverse, and far more stable in pricing. Lithium pricing, by contrast, has shown extreme volatility, swinging dramatically within short timeframes. For Tesla, predictable raw material costs mean predictable manufacturing costs, and predictable manufacturing costs reduce the need to build pricing buffers into vehicles. Over time, that stability tends to reach consumers, not always immediately, but inevitably. Of course, there is a question skeptics always raise. If aluminum-ion batteries are so promising, why are they not already in cars? The answer is energy density. Traditional aluminum-ion cells currently store less energy per unit of weight than lithium-ion cells. In simple terms, early versions would either be heavier or offer less range if used as a direct replacement. But Tesla does not design systems in isolation. Tesla redesigns entire architectures. Lower energy density at the cell level does not automatically translate to lower performance at the vehicle level. When cooling systems are simplified, when structural battery packs are optimized, and when protective overhead is reduced, large amounts of weight can be reclaimed. In some cases, hundreds of pounds disappear at the system level. And when weight comes down, efficiency goes up. When efficiency goes up, range comes back. So here is the real question, and it is not theoretical. If your electric vehicle could have a battery that lasts the life of the car, rarely needs repair, and is far cheaper to service, but your real-world range drops slightly, would you accept that trade? For drivers who charge at home and drive predictable daily distances, the answer may already be yes. For those who rely on long highway trips or have lingering range anxiety, the answer may still be no. And that distinction is exactly why Tesla explores multiple battery chemistries at once. Now let us talk about the part of EV ownership that rarely gets discussed, yet quietly drives costs higher than almost anything else: battery service complexity. Modern lithium-ion battery packs are engineered for safety first, repairability last. Cells, modules, cooling channels, sensors, and structural elements are often bonded together using adhesives designed to survive crashes, not to be disassembled. When a fault occurs, technicians frequently must remove the entire pack, disassemble layers, and work through systems that were never meant to be serviced in pieces. That process takes time, sometimes days, sometimes weeks, and labor costs climb fast. Aluminum-ion batteries allow for a different philosophy. Because the chemistry is more tolerant of heat and electrical stress, Tesla would not need to isolate every cell as aggressively. That opens the door to larger, more serviceable subpack segments rather than heavily bonded micro-modules. Imagine a battery pack divided into several major sections, each accessible without cutting adhesive bonds or fully disassembling the enclosure. If one section degrades, it can be replaced independently. Labor time drops dramatically, costs fall, downtime shrinks. There is also the issue of false positives. Lithium-ion systems rely on extremely tight thresholds. Minor sensor irregularities can trigger system-wide fault codes, forcing conservative service actions that escalate costs even when no real danger exists. Aluminum-ion chemistry operates with wider safety margins. Voltage fluctuations and localized heating are less likely to cascade into shutdowns. That means fewer unnecessary service visits and fewer precautionary replacements. For owners, downtime is an invisible cost that rarely shows up in brochures. A vehicle sitting at a service center is a vehicle not doing its job. Faster, simpler repairs improve ownership experience and protect resale value. Speaking of resale value, used EV buyers are becoming increasingly battery conscious. Once warranties expire, vehicles with sealed, complex battery packs face steeper depreciation. Buyers factor in worst-case scenarios, even if the vehicle has no current issues. A battery architecture designed for partial repair changes that psychology. When buyers know that a degraded section can be addressed without replacing the entire pack, confidence increases. And confidence supports stronger resale prices. There is even an insurance angle that rarely gets attention. Battery-related claims are among the most expensive EV insurance events today. Minor underbody damage can lead to full battery replacement because lithium-ion systems are treated conservatively. A more tolerant aluminum-ion system could allow localized inspection and repair instead of total loss declarations. Over time, that could lower insurance premiums, a hidden ownership cost many drivers underestimate. If Tesla successfully brings aluminum-ion batteries into production, the impact will extend far beyond chemistry. It will reshape how electric vehicles are built, serviced, insured, and valued across their entire lifespan. The final question is not whether the technology is promising. It is whether Tesla can scale it fast enough without sacrificing performance where it matters most. Would you trade a little peak range for a battery that lasts longer, costs less to repair, and survives real-world abuse better? That is the decision shaping the next era of electric vehicle ownership. If this deep dive helped you think differently about EV batteries and long-term costs, let us know in the comments. And if you want more breakdowns like this, where Tesla technology is explained through real ownership impact rather than hype, make sure to like the video, subscribe to TESLARIS, and help us push toward our next subscriber milestone.